our geology seminar, Department of Geological Sciences Geology Seminar. It's my pleasure to introduce you to Dr. Ignacio Sepulveda. Dr. Sepulveda received his Bachelor of Science from Federico Santa Maria University in Chile, and then did a PhD in civil engineering at Cornell University, finishing in 2017, and then came back to the West Coast to do a postdoc at Scripps IGPP with Jennifer Hassey. And today he's going to talk about the 2022 Tonga volcanic eruption, one of the largest volcanic eruptions in the recorded record. Take it away.
With Krakatoa. Thank you, Matt. Okay, so thank you very much for inviting me to this. I always wanted to do a talk here at a Geological Sciences building, so thank you very much. So, well, this is a work we started in January, of course, after the event, after January 15. And I would like to show you here how was all the scientific process to try to develop a new model for this volcanic tsunami or this type of tsunamis we are dealing with, and what happened in that process, which I think is very interesting. Of course, a lot of failure, so you will see a lot of errors from my side, okay, but I want to show you how we are learning from the errors during this scientific work, okay. So the Tonga tsunami was a tsunami that was created because of a volcanic eruption, okay. That volcanic eruption happened in January 15, okay. So what I got from my cell phone that Saturday morning was this advisory saying that a tsunami were coming to the West Coast. And I hear from the day before, from the night before, that a volcanic eruption happened in the Tonga area. But I said, okay, maybe this is not a big deal. Nothing will happen here. But then soon after that, I woke up at 7 a.m. with that advisory saying, okay, we will have a tsunami which will come to the California coast and all the Americas West Coast. I was super skeptical. I said, no, this won't be a big thing. But then after 9 a.m., we started to see the arrival of the first wave. We could see some videos from Santa Cruz, California, in which we could see actually there were some flooding related with the tsunami. And I was saying, oh my God, something was happening. And then during that afternoon in the time here in San Diego, my parents and my family started to call me and send me videos in Chile about the tsunami happening because of this Tonga eruption. And I said, oh my God, what is going on here? So again, as it happened for the Palu tsunami, in which with sure we have talked a lot about the Palu tsunami in Indonesia. Again, a tsunami caught us by surprise. Okay, we were not expecting something, and finally we were getting something important. Of course, that same day, I started to work with my numerical models. Basically, try to estimate a Gaussian shape at the source region and try to do a propagation of tsunami waves propagating over the water only on that time and arriving to the West Coast. And I was seeing that actually we were observing something related with a big source of tsunami initial condition in the Tonga eruption and creating these big waves in Chile and in the United States, okay? So as I was saying, sit tight and assess. Just wait what is going on with this tsunami and try to learn from what we are having in terms of data. One of the important data, of course, was the media. Okay, so this was the first news we were receiving about the tsunami that arrived to Southern California. Also in Peru, we saw a very catastrophic event related with an oil spill, in which actually there was an oil spill not because the tsunami was so big, but because the Peruvian authorities didn't raise an advisory and a warning related with the tsunami that was coming to Peru, and that was creating a huge cascading effect. But also, then we started to see that actually in other oceans, for example, in the Azores, we were observing tsunami waves, and that was super surprising for us. How a tsunami or a volcanic eruption creating a tsunami in the Pacific Ocean was creating something in the Atlantic Ocean. That was super surprising. And I was saying, oh my God, what is going on here? Nothing is working here. Okay, so everything was a chaos, was a lot of questions. It was a very first day of tsunami assessment, okay? So as a chronology of the events, here is just a summary about all what happened during those days. In January 16, Professor Esteban Greeley from Rhode Island University kept our attention in this email list that we have the tsunami scientists, which gather many people around the world. And he was saying, oh, maybe this is exactly as what we see in the 1883 Krakatoa volcanic eruption, in which also we created tsunamis. And from that, there are many papers talking about this tsunami generated by that volcanic eruption, in which the main mechanism which was proposed was atmospheric pressure, or an airway traveling in the atmospheric pressure, which was created because of the big explosion of the eruption. Certainly, in our measurements that we started to collect that day, we actually saw that those signals related with some perturbations in the water, related with a faster airway traveling all around the world because of the volcanic eruption. But we didn't pay too much attention. Actually, I was saying, I was telling my colleagues and the people who were working with me, don't worry, we have so very good fitting with the tsunami initiated at the volcanic propagating over the ocean, that maybe those are minor things. This is just secondary. We were saying, don't worry at all. Yep. In the atmosphere, yeah, a compressive wave traveling, which is related with the big explosion. That is there, which is a compressive wave and traveling with a velocity, with a celerity of 300 meters per second, more or less. So, but we acknowledged that we were observing that signal, but we didn't make any relation with the tsunami. We were saying this is a minor thing, don't worry about that. We have our big Gaussian shape in the Tonga volcano, and in United States and in Chile, we are having very good match. That's good. But still, we were having the open question related with what is going on in the Atlantic Ocean. And furthermore, what happened with actually the role of those disturbances created by an air wave. Okay, we were not so sure, but certainly our intuition was incorrectly sent us to the conclusion that that was a minor effect. Okay, so still pretty convinced about the classic tsunami propagation in the water. Then the game changers happened. In January 17, we started with my good friend Matias Carvajal from Chile. We started to analyze dark buoys. Dark buoys are sensors, pressure sensors located in the ocean, in the deep ocean. Okay, and from these signals, we started to see some important role of the waves which were associated with the air pressure. Basically, some important waves created because of the by the airway which was traveling over the atmosphere, and not only because of the wave traveling over the water. So then the dark buoys started to tell us, oh, maybe we have something wrong in our model. Maybe the airway in the atmospheric pressure was playing maybe an important role in this. Okay. Then in January 20th, we learned that actually the tsunami, after we started to recover the connection with the people in Tonga, we learned that actually the tsunami was not so high there. Was important, it created a significant flooding, but actually the island was still there. So basically that meant that our big Gaussian shape initial condition that we were using in order to explain the tsunamis in the United States and in Chile was inconsistent. There was no way to create such a huge Gaussian shape, because if that would exist, Tonga Island would disappear. So there was no reason to think about that. So then, oh my God, here we have a problem with our model. Then also, and actually this is the credit all of Matias. Matias called me one day at 5 a.m., which is around 10 a.m. in Chile. And he woke up me at 5 a.m. and tell me, hey, Ignacio, did you take a look about the tide gauges in Puerto Rico and in the Azores? And I said, no, why I should take care about that? Well, take a look at that thing. And he showed how the air pressure wave was completely correlated with the time of the arrival of the big tsunami waves in the Atlantic Ocean. So certainly what was happening in the Atlantic was mainly because of the air wave pressure wave traveling over the atmosphere. And then, oh my God, we need to restudy everything and we need to really think about what is going on here. And then, just to confirm, Vasily Titov from the laboratory at NOAA, from the Tsunami laboratory from PEMEL, Vasily Titov in February 4 presented the first tsunami model, which was coupled with the atmospheric pressure disturbance. And only for the dark buoys, Vasily Titov actually could show that in a very coarse grid in the Pacific Ocean, he could have a very good fitting or a reasonable fitting between the simulated tsunami because of the air wave traveling through the atmospheric pressure and the signal they were recording for the trailing waves in the dark buoys. Therefore, the conclusion that actually the air pressure was playing an important role for this tsunami. Okay, so the conclusion was that my classic tsunami models and my classic methodology in order to simulate tsunami was not working. Therefore, we need to restudy everything and we need to have a long-term study of this specific event. Okay, and also thinking about what will happen in the future. So at least in my case and how my brain works, I typically would like to follow this procedure in which, first of all, we need to understand and interpret very well the records of the tsunami and also from the atmospheric disturbances. From there, we need to jam about trying to find models in order to explain that thing that we are observing in our measurements. Okay, not only for water, but now also from the atmosphere. And third, we need to use those models explaining the event that we are studying in order to do a projection about what we would like to do in the future. For example, how we can include an analysis of this volcanic tsunami hazard in civil engineering design, for example. And for that, we need to create new tools for tsunami hazard assessment, which can take in consideration the uncertainty of the future, not only about the recurrence of volcanic eruption, but also about what are the properties defining the intensity of that tsunami that is created, and so on and so on. Certainly, this is a very long-term process, but I want to show you what we have been doing during the summer and since we had this tsunami. So I will show you these 3 stages and what we are doing and what are our next steps in terms of this volcanic tsunami. Okay, the first thing we did for this event, and this was very early, actually a couple of days after the event, we submitted this paper with Matias Carvajal, my friend from Chile. We started to download tide gauge records, okay? Typically, these tide gauge records can be obtained from the UNESCO IOC website, where you can get all the records from everywhere in the world. So what we did was to take that raw data of the sea levels, and we started to do an analysis of the wave in order to define what was the arrival time, what was the maximum wave, and which was the first wave that we observed in our analysis. And in this plot here, you can observe in very clear blue colors waves which were the first wave that we saw in the Pacific Ocean in blue, in light blue. And in very dark blue, you can see the same station, but now the maximum wave which we were observing in different stations in the Pacific Ocean. The blue colors are related with the Pacific Ocean and the red colors are related with stations in the Atlantic and in other oceans, okay? We were trying to isolate both groups of stations because we wanted to see what was actually happening in the both sides. What we could see is that actually the first wave that we were observing in different tide gauges in the Pacific Ocean or around the Pacific Ocean were actually having a very good correlation with the air wave. And the air wave is represented by this straight line that you can see here, in which for that we are using a velocity of 307 meters per second, which is more or less the celerity of that compressive wave traveling over the atmosphere. Okay, and we can measure that using measurement from pressure sensors around the world. And then I will show you some measurements that we are using. But the interesting thing is that only for the Pacific Ocean, you can see this straight line, and this straight line corresponds as the mean celerity of a tsunami wave traveling in the water. Okay, from this orange line, you can see that actually the maximum tsunami waves were arriving at the time you suppose or you expect to wait for a wave generated at the source of the volcano. Okay, and basically this is the reason why I was wrong in my first model, because when I was comparing the arrival time, all the maximum waves were actually arriving with a hypothetical source of a tsunami at the volcano and traveling in the water with a celerity equal to square root of GH, in which H is the water. Okay, so we were observing this and we were saying, oh my God, so for the Pacific Ocean, maybe the tsunami source was created in the volcano and started to propagate in the ocean. Okay, or maybe the primary role. Now, for other stations out of the Pacific Ocean, we could see some very representative and special stations. And here I am showing you Takoradi in Ghana, Ponta Delgada in the Azores, and La Mona Island in Puerto Rico, at the west of Puerto Rico. And for those stations, you could see that actually, here is not so clear, maybe it's clearer for you, but you can see that actually we have, this is the largest wave or the highest wave. You can see that actually in these areas, you are having a very important tsunami height out of the Pacific Ocean. And for those cases, those are arriving after the pass of the air wave. So certainly, maybe those waves are related with the air wave, not a tsunami source created at the volcano, which have sense. Okay? Okay. So this is the paper we wrote with Matthias. And of course, after this paper, we started to think, okay, let's now try to define or to build a model which can explain all what we are observing here. Okay. Okay, before we start working with the records, here you have some dark buoys which are located in the Pacific Ocean. Okay. And we need to analyze first the properties of this tsunami wave and this mechanism related with a air wave creating tsunami waves. So for that, I want to pay attention to three important fluid mechanics numbers. Okay, and probably my students, I have a couple of students here will recognize this. First of all, we have in this event a very high fluid number. Okay, in which the VP is the velocity of the pressure and square root of GH is the celerity of a water wave in shallow waters. Okay, and you can see that this value is very, very, very high for this event. What this means? That actually you have a air pressure which is pushing the water, but it's moving so fast that the water doesn't have time to react to that movement. Therefore, the mechanism in order to create waves with a very fast air wave is actually not so efficient. You cannot create a big wave when the air pressure wave is traveling too fast because the water won't react to that, won't feel. It feels like a big punch, but oh my God, what happened that? It was not like a constant pushing. It doesn't feel like that, you see? So that is a problem, but then I will show you how the thing finally can explain everything. Also, we have a phenomena which has a very low Mach number. Okay, if you see the sound speed in the water is much faster than the celerity of the air wave which is pushing over the water. What that means? Basically, that means that dark buoys located in the sea bottom will be able to feel that change of pressure that we are feeling from the airway. So pressure sensors at the bottom of the sea will be able to feel that pressure perturbation, which is good news, because from the dark buoys, we will be able to understand what happened with the atmospheric pressure. And finally, even thinking and observing that the volcanic tsunamis have a wavelength which is shorter to typical earthquake tsunami, still we can observe that that wave is sufficiently long so we can apply the shallow water approximation, and that means that the desnivelation that we have in the water surface will be able to be filled in the bottom of the sea. So therefore, if we are having a tsunami wave created by the volcanic tsunami, the dark buoy will be able to feel that or hear that wave, okay? Because we will create a perturbation in the sea bottom pressure. So having these non-dimensional numbers in mind, now we will be able to see what type of model we can apply in our problem, okay? Okay, so as I was saying many times, repeating, we have an air wave, which is a pressure disturbance, okay, which was created by this very explosive volcanic eruption, okay? This wave that is traveling over the ocean is a compressive wave, and that compressive wave have a certain celerity which is very close to the sound speed, okay? In this plot here, you can see many measurements of pressure which we obtain from a seismograph all around the world. This is coming from the IRIS dataset. So what I did was to take some pressure sensors from there, okay? Typically the one which is outside. Sometimes I had to use the internal one, but at the end, the difference, I couldn't see important difference between the both pressure sensors. And what we can observe here is that actually we can observe what is the speed or the celerity of that air, okay, which is around 307 meters per second, more or less. And you can see how the wave actually can be seen actually twice or three times in certain stations, okay? So the decay was not so rapid. Still, we could see the air wave like many times over the specific places, okay? Yep, Rujin. This one? This one? Where? Like you say that it's dispersion tail that you, this one? Ah, well, the thing is, and this is something that I already included in the model, but I'm not explaining those yet. I think because the celerity of the air pressure basically depends on the temperature that you have all around the world. So basically the temperature will define the celerity. So you can think that the temperature around the planet, the average temperature over the atmosphere can be seen as a water depth for the tsunami wave. So you will have some difference. And I was thinking that this second signal were actually some reflections of the air pressure wave with a place where you were having a strong drop of temperature. For example, in the North Pole for this case, yeah, because we were in winter on that side. However, the bad news is that I already implemented everything with a varying temperature in the world, and I could not explain yet this signal. But that is a good observation. Another thing that also I was worried is that in my model, I'm using a non-dispersive model for the air wave, but you can maybe see that you have some dispersion tails in the pressure wave, okay, which are not considering yet. And I'm still thinking if I include it or not. So, but very good observation. Okay, but from this plot, the take-home message is that we can obtain the celerity of that wave, okay? Okay, so in terms of how we have addressed the problem of the tsunamis created by atmospheric disturbances or pressure disturbances, of course, we have many papers talking about what happened in 1883 for the Krakatoa eruption. Okay, for people who doesn't know, the 1883 volcanic eruption actually also created a big tsunami. Okay, And certainly for this event, we are thinking that it's exactly the same mechanism. We are having a same event, but now in another location and related with another volcanic eruption, okay? But the important thing here for this event is that actually we don't have an extensive amount of data in order to model and to try to infer some conclusions about the Krakatoa volcanic eruption in 1883. Certainly there are some pressure sensors, and the people who have studied Krakatoa tsunami also are acknowledged that there is a significant amount of data which can appear in all these papers that I show you here. However, the important thing here is that I would say that the paper, for example, the paper from Ryder and Press was saying that this was only atmospheric disturbances, and actually they were trying to find some coupling modes in order to explain the big tsunami waves that they were observing in different places in the ocean. For this tsunami, the new tsunami from January, we started to check that possibility and that mechanism that Ryder and Press was suggesting, and we didn't believe too much because we were not observing that in our models. We were not observing like a very magical slower mode in the pressure creating a big tsunami, or at least it's not evident for us. But from all this paper, we could see one paper which is not very popular, and this is the paper of Garrett, who was also studying the Krakatoa tsunami. And Garrett was saying that actually the changes in the bathymetry were maybe playing a role, increasing some tsunami waves. Probably the mechanism of the pressure creating the tsunami waves was the same as what I was explaining before with these non-dimensional numbers, but the bathymetry change maybe can play a role creating bigger tsunami waves. And that is what I will show you now. I think, yeah. So I think this is the best way to try to explain. I would say that all the data is pointing to this explanation. I haven't seen something contradicting this way to model the problem. And I want to show you here. So for example, let's imagine that we have an area, a center. This will be an animation, okay? Then we will run it, but I want to explain you before. Let's imagine that we have a volcano here, okay? Let's imagine that volcano created some flank collapses, created some changes in the bathymetry, and that created finally an initial condition in the volcanic zone, okay? Just because we are changing the geometry of the seabed, we will perturb and we will create a tsunami wave there, which will start to propagate because of gravity. But also, as the case of this event, let's imagine that also we will have an explosion, and that explosion will create a pressure perturbation which will travel all around the ocean, okay? And for the bathymetry here, I will use a very simplified bathymetry. Let's imagine that we have a constant depth, but close to the volcano, well, at mid distance, we have a trench, okay? An area with very deep water. So let's run the animation. Okay, let's repeat it again. So you will see that you will have a pressure wave traveling, which is represented by the red line, and that pressure wave will be creating a little tsunami wave. Okay, and you will see how this deep region are creating actually a tsunami, which you see here. You see, and now you are increasing and then decoupling that. So what happened? What will happen is that we think that volcanic eruption actually is creating three types of tsunami. The first tsunami is the classic tsunami created at the source region, created by a deformation of the seafloor or any mechanism creating an initial water elevation, which is different from the mean sea level. Then, because of the air wave, that air wave will create, while it's propagating, a very tiny wave, which is traveling with the pressure wave and which is coupled, okay? But also in deep regions, you will have the possibility to create bigger waves But after you pass that deep region, those waves start to decouple from the air pressure. And this is the type of wave that we were not observing when we were running our first model. Because indeed, next to Tonga, there is actually a region with a very deep water, which you were able to create that wave. Okay, I will show you a video of the real problem. Okay, well, let me explain a little bit about my, okay, so thinking on those very simple mechanisms, what I did was to take the Comcode tsunami model, which is a tsunami model or a code which was built with Philip Liu and the students of Philip Liu. Philip Liu was my advisor. And of course, because I'm coming from that department, I have devoted many time like modifying that tsunami code. Okay, and one of the modifications I'm doing is trying to include pressure forcing on concrete. Okay, but this is not so simple. Well, it's very simple to add the pressure terms in the nonlinear shallow water equations. Actually, super simple to do that. But because you are dealing with a global scale event, this means that you have to make many changes into the code. For example, I need to include periodic boundary conditions so I can have a propagation of a tsunami all around the world. Okay, Comcode was not prepared to deal with global tsunamis because always we were dealing with very small domains of our tsunami models. Okay, this is one of the things that I considered a couple of months ago, which is a celerity field for the pressure. So basically we are adding the temperature as an input, and for that we can make a propagation and a calculation of the air wave propagation all around the world. Basically we are trying to solve for the land wave propagation using as an input data the temperature, which is basically the problem of solving the linear shallow water equation coupled with the nonlinear shallow water equations of the tsunami. Okay, we are running both in parallel. Okay, so we need to build this scheme in order to solve for the land wave or the air wave in parallel to the tsunami wave. Of course, we keep some classic initial condition of the tsunami, so we can model the initial condition of a tsunami in the volcano. And of course, also we need to modify the output or the type of outputs of the model in order to get information related with the pressure wave. Okay, because we need both in order to do our analysis. Okay, so this video is not working. Yeah, let me see if I can make it. If I can make it work. Yeah, well, you can visit my YouTube page to see the videos. Unfortunately, I cannot run I cannot run the video. But what we can see is that this is a global simulation in this new Comcode version. And what we have is that in this plot, I can simulate the propagation of the air wave over the atmosphere. And in parallel to this air wave, which is perturbing the water, you can see what happened with the water. Okay, and what you expect to see is that you have a leading wave of the air wave creating tsunami waves. And you know, let's put the video because otherwise you won't believe me. Let's do it very fast. There you are. It has a lot of views. You can see that. So in the top panel, you have the air wave, and in the bottom panel, you have the tsunami waves. And you can see how the air wave is creating the first perturbation in the water, but actually behind that, you have a higher wave. And what you can see is that that higher wave, higher than the leading wave, is actually created here close to the Tonga volcano. Basically, that big wave that we are observing in Chile and in the US was not created in the volcano, but it was created in the region in the Tonga Trench. So you had a big wave created in the Tonga Trench, and that was the big wave that was traveling to the US, and I was traveling to Chile. And that is why I had the confusion in my first model, because I was putting a Gaussian shape in the volcano. And that Gaussian shape was actually very close to the Tonga Trench. But now with the generation of the tsunami at the Tonga Trench, you will be able to explain what was happening with the tide gauges all around the Pacific Ocean, or most of the energy. Okay, you will see that actually still we need some deformation in the volcanic region in order to complete all the energy that we can observe. Okay, so basically here, the same video that you saw in YouTube here. Here you have the pressure anomaly or the pressure disturbances. The red line is the simulation of COMCOT, and in black you can see the records for many stations. And here what you can see is the tide gauge. Again, the black line is the records of tide gauges around the Pacific Ocean, and the red line is basically the simulation of the model. So basically, we are doing a fair job, at least in the middle of the ocean. Okay? And now you can see a lot of papers which are doing more or less the same mechanism, and they are showing that they are getting the same. Okay? Okay. Let me jump now to the map. Oh, sorry, Heather, don't worry. I can manage this here. Okay, maybe. Okay, so what happened here? As I was saying, areas with deep waters will be able to allow the air wave to create big waves, or big tsunami waves, or significant tsunami waves. And if we take a look of the oceans, and we try to highlight the place with high depths, we see that we have this area, which is the responsible of creating the big waves, which finally were traveling to Chile and to the US. Also in my videos, you can see that this region is also creating an important tsunami wave, which are traveling to the north. In Puerto Rico, next to La Mona Island, where we are observing significant waves, we have that deep region, that trench, which is actually helping to create big waves. Okay? Where in Ghana here, we cannot see anything, and close to the Azores, neither, okay? But we are thinking that something is happening. Maybe they are receiving waves coming from other sites. We are still not sure, okay? We are studying those stations where we were observing big waves. Also in Japan, take a look, for example, or in Asia, how these trenches actually can help to increase the size of the tsunamis created by the pressure wave. Okay, so these are the pictures of the three stations where we observe big tsunamis out of the Pacific Ocean. We have Takoradi in Ghana, we have Ponta Delgada in the Azores, and we have Isla Mona in Puerto Rico. For the case of Takoradi and Ponta Delgada, when we were running our simulations with this COMCOT, which, by the way, I'm using COMCOT because also another feature of that model is that we can include nested grids. Basically, we can increase the resolution next to the coast, so we can get more details of the tsunami propagation. And what we could observe is that when we were running our first model in Takoradi and Punta Delgada, we were not obtaining the big wave heights that we were observing in the order of 1 meter. They were much smaller. So what we started to do, we started to collect more detailed information of the bathymetry. For example, take a look about what happened in Ponta Delgada. The tide gauge of Ponta Delgada is located inside this harbor. And actually what is happening there is that we started to have a coastal resonance of the tsunami wave. Okay, and we are trapping energy inside that marina. And that is one of the reasons why we are observing high waves. And I will show you the simulations on those locations. So we have to take care for a volcanic tsunami of two things. First of all, we need to take a look about what are the areas with deep waters where we can make more efficient the creation of tsunami waves. And second, we need to take care even more, I think, than earthquake tsunami about what is the geometry of the coastal areas, because these waves will be shorter than the typical earthquake tsunami, and probably they are more likely to start to have resonance processes at the coast. So basically, it's a big headache for us, because first we need to pay attention carefully about what's happening in the global scale, but also we need to take care about what's happening in the very small scale of the coastal area. So that is a very important thing that we need to consider when we are doing volcanic tsunamis assessment. Okay, so here I will show you what we have so far working with our new code for volcanic tsunamis. And in this plot here, I want to show you and attract your attention to a station which is located in northern Chile. Okay, this is the station of Chañaral. Why I picked Chañaral? Because here, in that January 15, we could measure with the tide gauge a wave height of about 3 meters. Actually, it's the highest of this event, a huge tsunami. Okay, so of course, first of all, maybe it's related with a region, a deep region close to that area, which was making efficient the creation of tsunami waves, but also you had to maybe have a geometry of the coast which was good in order to amplify the tsunami wave. So in this plot here, you have the pressure, the simulated pressure in Chañaral, Chile, and here you have in blue the record and in red the simulation. So you can see that the arrival time is very good and the amplitude is reasonable with respect to what we were measuring. This was the pressure wave, but then now we will receive the wave which was created in the Tonga Trench. So the wave created at the Tonga Trench is arriving and bringing a huge tsunami. And then in our simulations, we are not explaining this record which is coming after that. Why? Many reasons why we are not fitting the rest of the signal. But a good thing related with this specific problem in Chañaral is that for this model, right now, I'm only considering the pressure perturbation. Maybe the other piece of the energy is related with some tsunami source created in the same place of the volcano. Or maybe the problem is more complex and we need to deal with the dispersion of the airway, maybe, which maybe will have playing a role increasing the tsunami waves, which we are not sure yet. For the Azores, this is a simulation in Ponta Delgada. So Ponta Delgada is located, the Azores is located here. Here you have a zoom of the island of the Azores, and here you have Ponta Delgada, which is the marina I was showing to you, in which we could obtain an acceptable resolution of bathymetry. So in the blue ones, you have the airway, and in the bottom graph, you can see the tsunami wave. So this one requires some time because we need to wait for the airway to arrive to the Atlantic Ocean, and now it's arriving. So now you will start to see the tsunamis arriving with the airway to Ponta Delgada. This is the tide gauge red simulation, blue measurement. And what you can see in Ponta Delgada? Resonance. You see that it's more blue or more red? So basically we have a coastal resonance there. Okay, the bad news is that for the first burst of wave, we are having a very good job. We are actually capturing the same amplitude, but there is a second burst of wave, which is actually related with the highest wave in the Ponta Delgada, which we haven't captured yet with our model. And again, we need to review what happened with our simplifications and what we are missing in order to get that second burst of waves. Okay. So this is the second part. I want to go briefly in a third step, which is related with the tsunami hazard assessment. So I will go brief here. So everybody knows that tsunamis have a very low recurrence. Okay. And actually here you can have a plot about what was the death toll of the last tsunamis in the US. And actually it's pretty small, okay? However, the problem is that right now in coastal region, we have 40% of the world population living within 100 meters from the coast, okay? And also we know that tsunami is responsible of the 10% of the economic losses related with natural hazards. So therefore, we need to do something about it, okay? And typically I explain this point. For example, I can show you that in our lifetime, actually we have an 8% of probability to face a 1,000-year event in our lifetime. So typically when we are talking with tsunami, we are saying, oh, we will design a nuclear plant for 1,000-year return period. Actually, that is very low, because if we consider our lifetime, the probability to face that event, thinking that it follows a Poisson process, is actually a 7.6%. That is pretty high, okay? So that is why I always tell my students, we really need to try to make this probabilistic tsunami hazard assessment, because very long return periods actually will show that actually you have high probabilities to be affected by that, okay? And the economical losses related with tsunamis are, we know that they are pretty high. Okay, so in terms of probabilistic tsunami hazard assessment, in which we can estimate those probability, in our research group, we typically work with probabilistic tsunami hazard assessment. For example, this is a probabilistic tsunami hazard assessment considering estimating the probabilities of flooding in Hong Kong because of earthquakes in the Manila subduction zone. And also right now we are trying to work with compounding effects. For example, what is the effect of the sea level rise in tsunamis, which is actually when you have middle tsunamis with middle intensity, the sea level rise is pretty important. For the case of volcanic tsunamis, we really need to consider what are the sources of uncertainties in our model. If we are thinking that in the future, we will need to project what is the volcanic tsunami hazard. And for that, we can try to make models of the uncertainty. For example, here you have a sensitivity analysis I did in terms of the average temperatures for the world, which have an effect, or which is the input information in order to see what is the air wave propagation. And we can see that actually we have some slight differences if the eruption, volcanic eruption happened in summer or in winter. Also, previous work I did during my postdoc was related with the uncertainty of the bathymetry, in specific the bathymetry derived from satellite altimetry, okay? And those are aspects that we need to consider, especially for volcanic tsunamis, okay? And also another important thing is the cascading effects, okay? Sometimes the tsunami is not the problem. The problem are the effects which are triggered by the tsunami. For example, you can see oil spills, you can see the drift of vessel, or also flooding of critical infrastructure. Okay. So I think I will finish here. So as a conclusion, this event was super important because we have a great amount of data, at least much more than the 1883 Krakatoa tsunami, and this allows us to understand better this mechanism. We also finally could verify that the land wave or the air wave is important. So I was completely wrong that first day after the volcanic eruption. And also working with this model, we can understand now the relevant variables in order to do a projection or a prediction of the tsunami hazard assessment in the future, okay? So as you can see, still we have many open questions. And for this, I'm working still with Matthias, also with Professor Duncan Agnew at Scripps, who are helping me a lot in terms of the forensic work, trying to get data from the 1883. Okay, and well, here two pictures. I wanted to show my two undergraduate students who are working with me in probabilistic tsunami hazard assessment, and all the work we are doing in this new lab. And that's all. So thank you. Just a little picture of my postdoc work.